Alright, so looking at the shortest distance from a line to a point. Here we have a case where a ship is sailing along a path and we want to find where is it going to be closest to this point on shore, this port. And while this is kind of a contrived example, obviously I'm sure you can kind of see the application to any type of a thing, whether we're talking about planetary motion or we're talking about any other kind of motion, and we want to find out, hey, where's the shortest distance, or where is it going to be closest to this location? Often, because that'll be maybe the easiest way to intercept that object or something like that. But if you look at our diagram here, we have 2 points, and this is our ship going A through R, okay? And notice I gave it the velocity vector B. And anytime we're measuring from a point to a line, when we're talking about the distance, we're talking about a distance that is the shortest distance, and that shortest distance will always be the perpendicular, okay? And actually the proof of that is really simple. If you took any other distance that wasn't perpendicular, you would then have a right triangle, right? And if you compared the length of this to the length of this is the hypotenuse of that right triangle. The hypotenuse is always longer than either of the legs, okay? So we know that no matter what point you pick on this path, if it's not the one that makes it perpendicular, then it's not going to be the shortest distance, okay? So that's just a quick rationale here behind why we're doing the perpendicular, okay? But as a matter of review, since we're talking about vectors, how did we get perpendiculars?
What do you mean, how did we get perpendiculars?
How did we know if 2 things were perpendicular when we're talking about vectors?
If the dot product is 0.
There we go, the dot product, and that dot product has to be 0, okay? So basically what we want here, they just placed R on this diagram in an arbitrary place, but what we want here is the vector from our point to that point R to have a dot product with the velocity vector of 0, okay? We don't need to find vector AR because we just have a velocity vector B, okay? So to give us this kind of a picture of what this is going to look like, here's our perpendicular, there's R, and we want vector PR to be perpendicular, and I'll draw it right here, to vector B. Okay, and that only happens if the dot product is 0. Now, one term that you ought to be familiar with is this term, foot of the perpendicular from P to the line, okay? The foot of the perpendicular. When they use that term, they're talking about the point that would make a right angle, okay, from P with the line, okay? So that point R is that foot of the perpendicular, okay? Now, let's take a look at how we would go about doing this, all right? First of all, we need to get a vector equation, okay? We need to get a vector equation for our line, and obviously we need coordinates for a point, okay? So here's our line. It has a vector equation, xy equals 1/2 plus t times, not 1/2, sorry, the vector 1, 2, plus t times the velocity 3, -1. Now, I put on here the key is to define R as some point in the direction of the line from P at an unknown time t. Okay? So I'm going to define R, okay, using my vector equation. Alright? Yes.
What's that sideways pitchforky thing?
Oh, that. That says T is, you'll notice, if you can see here, the R has kind of double lines.
Oh yeah.
That stands for real numbers. That is, this means that the T is an element of the real numbers.
Okay.
Basically, it's just saying T has to be a real number. We can't do this for complex values of T. Good question, though. Alright, so if we think about this, we want, if you look at the points here, x, y, our parametric equations are 1 plus 3t, and y is 2 minus t. Alright, I'm actually going to use those as the coordinates for r. Okay? So 1 plus 3t, 2 minus t is going to be my point r. Now the reason why I can do that is because, or the reason why I want to do that is because I know my velocity right here is the vector 3, negative 1. Okay? I want vector PR so that I can then find a dot product, set that dot product equal to 0, and then that will help me solve for t. Okay, what t will make that dot product equal 0? So let's look at this whole process. Remember when we're finding the vector from P to R, we take the coordinate of R and subtract the coordinate of P. Alright, so 1 plus 3t minus 5 is a negative 4 plus 3t. So that's the horizontal component of that vector PR. And then I take 2 minus t, and I subtract the negative 1. So that'll be plus 1. I now have 3 minus t. Okay.
Shouldn't that be reversed? Because otherwise it's parallel and not perpendicular. Because you want PR to be perpendicular, right?
Well, yeah, we haven't done the perpendicular aspect of it yet. Here's the perpendicular aspect. We've got to
okay,
do.
I was getting confused because in that box it says find exactly the shortest distance from P to the line.
Yes, and R is a point on the line. That's why we used these parametric equations as, so I know that point's gonna be on the line because I used the parametric equations for its coordinates. Okay? So now I'm gonna do V dot PR. Okay? And do you remember how we do dot product? Okay? Yeah, multiply those horizontal components, so 3 times a negative 4 plus 3t. We're going to add to that the product of the vertical components, so negative 1 times 3 minus t. Okay? So
Why is 3 negative 1v?
Remember our vector equations are position, which if I remember right, did they use R or something? Doesn't matter. I'm trying to remember exactly what letters. The letters don't technically matter, but just to make it match the IB that you'll have. A plus TV. Yeah, okay. So what you have here, you have a starting position, and then you have to add to that starting position vector, which is the 1, 2. We're starting at the position 1, 2. We're adding to that our velocity times however long we're going at that velocity. So whatever part is multiplied by the t, that's your velocity vector.
Thank you.
Why is A a vector as well?
Because, here's the thing, you can think of it as a point, but remember we said all points can be written as position vectors. A position vector from the origin.
Yep. Okay.
Yeah. So it's just a way to make this work, because technically you can't add a point to a vector, but you can add a position vector to a vector. Okay. So. Alright, so here's what we have. We know the dot product is now negative 12 minus 3, that's negative 15. 9t plus t is a plus 10t. And we want that to equal 0 in order for those to be perpendicular. Okay?
So you add 15 to the other side,
Mm-hmm.
and
Yeah.
then you get that t is 2/3.
Well,
Or 3/2.
3/2. Yeah.
Where did you get the 3 and the negative 1?
I got the 3 and the negative 1 because we want to find the dot product between the velocity vector of the line, the direction of the
so You
line.
just ignored the initial position.
Yeah. Okay. So now we want the shortest distance from P to the line. So now we found T. So now we can actually tell what the point R is. Okay. 3/2 of 3 is 4.5 plus 1. That's 5.5. And 2 minus 3/2 would be 1/2. Okay, so now I know what point R is.
And then you just solve for PR to find the distance.
Yeah, we also know what PR is, and if we find the magnitude of PR, then that'll give us our shortest distance. Okay, so I guess we didn't technically have to figure out what the point R is, but.
Well, you did because it says define R. Or is that 1
Oh,
plus?
that's just that's where we started
Is that 1
defining
plus 3t and then the 2 minus t count as defining it, or do you have
Yes.
to actually put in the numbers? Okay.
Yeah, that's it. So let's see, negative 4 plus 4.5 would be 1/2. And 3 minus 3/2 would be 1.5. Okay, so now that is vector PR. And like I said, we need to find the magnitude of that vector. Okay. Someone remember how to find the magnitude of the vector?
The square root of x squared plus y squared.
Yeah, there we go. The square root of, if I can write a p, there we go. So it's going to be the square root of the 1/2 squared plus, I'll write it as 3/2 squared. Okay?
Which is 0.25 plus 2.25, which is the square root of 2.5.
So you've got And it may be easier to keep it as fractions, 1/4 plus 9/4.
Which would be 5/2.
Square root of 10 over the square root of 4, which is 2.
Okay, that works too. That's a pretty simple way to do that.
I left it in terms of quarters so that you could actually take the square root of the 4. Okay, so that's the shortest distance. Root 10 over 2. And by the way, whenever they say exactly, they're saying
No decimals.
no decimals, yeah.
Unless the decimal's exactly.
Yeah, unless
0.25.
it's exact, yeah. So, you would just leave your answer like that. That make sense? Okay. Now, I wanna do some other applications here. I wanna give you guys a few minutes to try one or two of these on your own, or with a partner here. So we're gonna stop the video, hold the second part, and we'll let you guys just take either A or B, either C or D. In fact, you know what, just for consistency, let's go ahead and do A and C. Together with the partner. I'll stop it and we'll look at this in the second part.